Welcome to See the Unseen.
Hi, I'm Kalina Naidoo and I'm a postdoctoral researcher in the cavity working with Richard Wade Martin. Today we'll be looking at iPSC-derived dopaminergic neurons, and we'll be looking at how we investigate Parkinson's disease using the cell model. So our lab is interested in Parkinson's disease. We work with cells, and specifically we work with iPSCs. What's really cool about them is that you can just take a skin sample from a patient with Parkinson's disease and they can actually induce this skin cell to become a stem cell. And then what we do is we take that stem cell and differentiate it into a neuron, a brain cell, and specifically these neurons that secrete dopamine. Our specific interest is in the genetic mutations that result in this disease. Only about 10% of the disease have this genetic mutation background. Most of the cases we refer to as sporadic causes because we don't really know exactly what causes the disease, but we know the hallmark of the disease is the loss of these brain cells, neurons, as well as the accumulation of a specific protein called alpha-synuclein, which we think might have toxic effects.
So that protein is kind of collecting in the brain in certain regions
and
then damaging a certain type of nerves.
Neuron. Yeah. And so this specific neuron is in charge of releasing dopamine, and dopamine is very important for movement in our body. That's why some of the symptoms of Parkinson's disease has to do with, tremors, rigidity. It's also a movement disorder as well as a disorder that is related to cognition. We're hoping if we understand the architecture of these genetic mutations, we have a better understanding of how to then think about interventions and treatments. My specific interest is the GBA mutation. This specific mutation is the N370S mutation, and this results in a decrease of a specific enzyme called GCase. And so we're looking at compounds that will increase this enzyme.
How did you get into this sort of research?
I'm from South Africa, and we have an HIV crisis a few years ago. When I was doing my undergrad, I learned about HIV-associated dementia. And I thought this was super sad because it was not only that people had this, at the time, lots of people were dying from the disease, but then they would also get dementia in their 30s and their 40s. So I was very interested and started working in HIV-associated dementia research, and then looked at Parkinson's, and Richard had super interesting ideas. He allows you to flourish quite a lot and take your ideas and incorporate it into the project, and it's a really nice facility in the cavity as well.
And so what are we going to do today?
What I'll do is I will treat my cells with a compound. This will result in the increase of, hopefully, of this enzyme, and then we'll be looking at this through the microscope.
Yeah, that's really interesting.
This is the iPSC tissue culture room, so we only differentiate stem cells in this room into neurons, and it's because this process is a 3-month-long process, and it takes quite some time for them to differentiate. And
so we need to keep them safe.
We have to keep them very sterile. It's very sensitive to, once it gets contaminated, it can't be used. It's very sad. It does happen. You can be nurturing them for 2 months and then it gets contaminated. So these cells are actually about 4 months in the making.
What are we seeing here?
So these are dopaminergic neurons.
Oh,
I like this.
Yeah.
They make me happy.
Yeah.
So they're all looking healthy, and they look like the morphology we expect at this period, because it's really important. We know certain things happen at certain times of the differentiation, and so it's really important to get those time frames correctly. So the specific enzyme I'm interested in, it takes about 30 days of them maturing into neurons for it to be active and able to be noticing the changes in that enzyme. Now that the compound or drug has been dissolved, we're going to prepare what we will call the sauce plate, because this is what we'll then use. So the robot will take the liquid from here and put it onto what we call the destination plate.
Yeah. So this is the robot.
Yes.
Yay!
This is the robot. So how the echo works is it works with sound. So it actually is flicking really, why we don't use a pipette to take the liquid out and put it in, is that we're using really, really small volumes. So the echo can actually flick as low as 2.5 nanoliters.
Oh.
And so it just uses sound waves to flick the liquid from the source plate to the destination plate.
Cool.
So actually the source plate will be like this, and the destination plate will be like that, and
Like
the
upside
liquid,
down?
yeah, and it'll be flicking it into it. It's more precise than doing hand pipetting. Yeah, so it's all done. So these are our dopaminergic neurons, which we've added the treatment and the dye to look at the specific enzyme, GKs. And now we're going to see whether there is a visual difference in the GKs levels between these.
So what are we actually seeing here?
So this is dopaminergic neurons, brain cells that get damaged during Parkinson's disease. This is the nuclei of the cell. So you can see they're nice round blue nuclei. You can see a lot of like axon terminals, which are hallmarks of neurons. You can see a lot of connections, which is how the cells like to live. They connect to each other. And this is how the signaling happens between the cells.
Yeah.
So the green, what we're seeing is the cytoplasm around the nucleus. And this is just to show that these are healthy cells. And then the yellow that we're seeing, this is the GK's enzyme that we're interested in.
Yeah, it looks a bit like it's gold.
Yeah,
flecks.
it's quite pretty.
Yeah, it's very
and
pretty.
so these little spots, they're spots that are specific to a cell organelle called the lysosome. It helps with clearance of stuff that we don't need in the cell. There's a theory that this GK's enzyme actually helps with alpha-synuclein clearance.
Yeah. Huh?
And so that's why we're interested in this specific enzyme.
Yeah, very cool.
What's really cool about iPSC dopaminergic neurons is that they actually have the genetic background of the patients that we've taken the skin sample from. And so it's like looking at the genetic background of the patient without meeting the patient. Like it's completely non-invasive. Now I just tell the program anything that is of this fluorescence and this size is what I'm looking for, and it just counts it. And so you have the amount of cells you have, the amount of spots that represent the enzyme, and then you can compare whether the patient with Parkinson's has less spots than a healthy control, someone who does not have Parkinson's. And you know, this assay confirms that they actually do have less enzyme. And so it's a very robust way because you can actually physically see this enzyme difference between healthy controls and people with Parkinson's disease.
We are soon saying goodbye, you see. He's going back to Finland to do amazing medical and research things.
Okay.
And so we just wanted to give you a little token of
Oh,
appreciation.
You hit that so well.
It's from all of us, also the people behind the camera, who do so much work for this channel.
They do.
Yeah.
No! What?
That's so cool.
That is very cool.
So, lots of luck to you in
No.
Finland. And remember us.
Of
here
course.
At See the Unseen.
Oh, thank you. Thank you so much for taking us for a tour of the lab.
My pleasure.
Yeah, I found that robot really exciting.
Everyone is very won over by the robot.
Yeah.
I'm quite personally excited by the fact that you're taking stem cells and turning them into like literal neurons.
Yeah.
I think that's cool.
Yeah.
Do you think by the time you leave here you'll have grown like a whole brain's worth of neurons?
That's a very
Or maybe
interesting
fewer.
question. I hope not, to be honest. Like, it is quite a time-consuming process.
So you're here for the next 2 years, continuing on with this really cool work. What do you imagine doing after that?
I see myself as a researcher. I enjoy research. I enjoy academia, and one of the reasons I enjoy academia is because I love teaching. I've heard of some really good programs in Europe where you can do like 50% teaching, 50% research. Right now it's like 150% research. I would like to set up a Parkinson's research group in South Africa, back home. A lot of the research comes from the West, and so we don't have a lot of like genetic data from an African perspective, and I really like to set that up. There have been links between things like demographics and the occurrence of Parkinson's. It'd be interesting to delve into that from a South African perspective.
We'll keep an eye out for the Naidoo group in
Naidoo
South
group,
Africa.
yeah.
Can't wait.
Yeah,
and best of luck with your work, both here and wherever the future takes you.
Thank you.
Thank you very much for taking us.
Thank you.
See you in the next episode.
Bye.
Bye.